Hi everyone, I am Gauri PS, lecturer, Department of Radiography, Global College of Allied Sciences. Today we are going to discuss about rotating anode X-ray tube. First, in 1933, a rotating anode X-ray tube was invented, that in which that anode will be made to rotate before when the electrons are emitted from the cathode. So actually it was developed to increase the heat loading with higher X-ray output. And in these tubes, the electrons will be transferring their energy over a large area of the rotating anode. And usually these rotating anode tubes are larger in size, but the principle and its function are similar to that of an stationary anode X-ray tube. Usually this rotating anode X-ray tube will be using a spinning tungsten rhenium target as their anode to disperse the intense heat which is generated when they are hit by the electrons and allows for higher X-ray output and longer exposures which is compared to the stationary anodes, making it an ideal for CT scans and general radiography. An external motor, that is stator, will be spinning an external rotor and it will be rapidly turning the anodes to spread their heat across a large surface and will be preventing the damage and enables a greater X-ray intensity for detailed medical imaging techniques. Next is about working principle. First is about electron production. A heated tungsten filament, that is the cathode, will be releasing an electron cloud via a thermionic emission process. That is then a high voltage potential, that is about 50 to 150 kilovolt, will be applied between the cathode and anode and they will be accelerating the electrons towards the anode. Then X-rays will be production. That is when this high speed electrons strike the anode's target material, that is usually a tungsten rhenium alloy on a molybdenum or a graphite base, there will be approximately 1% of its kinetic energy will be converted into X-rays while remaining 99% will be converted into heat and heat dissipation. The anode will be in the form of an beveled disc that is connected to an rotor. An external stator functions as an electric motor and it will be spinning the rotor and anode at a speeds which is up to 10,000 rate per minute. This rotation will be spreading the electron beam's impact across a larger circular focal track and it will be preventing the localized spot from melting. Next is about cooling. The entire tube will be immersed in an insulating oil so that it will be absorbing the heat from its tube housing and cooling fans or water circulation for further managing the temperature. Then next we will be looking about the parts. Usually the rotating anode X-ray tube consists of cathode, focusing cup, anode, rotor, anode stem, bearings, and next is about vacuum envelope, etc. First we will be looking about cathode. A coiled tungsten filament will be kept inside the focusing cup that will be emitting the electrons. Usually the rotating and X-ray tube consists of a cathode and anode and they will be kept within a glass bulb. The cathode is a tungsten filament which is offset from the long axis of the X-ray tube to face the target nearer the periphery of the anode disc. Usually the rotating anode X-ray tubes are fitted with two filaments, that is one is larger and the other, that they will be placed side by side in the cathode assembly. One filament will be designed to focus the electrons on the larger area of the anode which will be requiring the heavy tube loading, and the other filament will be used to focus the electrons on a smaller area of the target. Usually, this type is used when high resolution is required. And both the filaments should be focusing on the electrons on the same part of the anode so that the angles for these two filaments so that each filament will have a separated focal spot. Usually a smaller angle is used with the smaller focal spot. Usually the small coil is made of thoriated tungsten, and when the machine is turned on, a small amount of current will be flowing through this filament and it will be heating, which in turn produces the electrons. Next is about focusing cup. Usually a metallic strand contains the two filaments. Usually they are made from nickel, which contains a negative charge. It is usually designed to repel and contains these electrons. Usually the focusing cup, it is also called as a cathode block, which will be surrounding the filament, that is, it shapes the electron beam's width. That is usually used to focus the electrons on a smaller area in the anode. Actually, there are two ways by which the focusing cup is energized, that is, namely by unbiased and biased. In unbiased setup, same voltage is applied to both focusing cup and filament. In this type, the electron spread is wider and the focal spot width is larger. In biased X-ray tube, the insulated focusing cups are used and it is given more negative supply, that is minus 100 volt than the filament, and it will be creating a tighter electric field around the electrons and they will be reducing the electron speed and it will be giving a smaller focal spot width. Thus usually the focusing cup width will be determining the focal spot width and the filament length will be determining the focal spot length. Then next is about anode. An anode disk is usually made up of a tungsten rhenium on a molybdenum core with a graphite backing, as it will be rotating rapidly. A positive charged rotating anode disk assembly is usually made of materials with high melting points and thermal conductivity, and at the other end of the tube an anode will be connected to the high voltage supply, and this will be allowing the electrons to accelerate up to a voltage of 200 kilovolt. When the electrons arrive at the anode, they will be gaining an kinetic energy that is of 200 kilo electron volt, and only 1% of this kinetic energy will be converted to X-rays, and the balance will be converted, that is balance 99% will be converted to heat energy. Therefore, to avoid overheating, the anode will be spun at an 3000 rate per minute, and sometimes it will be water cooled. So, anode is made in the form of a large disc of tungsten, or it is made up of an alloy of tungsten. Usually it is a saucer shape, and this track, that is the target track, will be nearer to the periphery of the disc, has a maximum length, and the track is a mixture of 90% of tungsten and 10% of rhenium, and will be reducing the crazing effect which is caused by the thermal stress. Usually the modern rotating anodes are made up from alloy of solid molybdenum, titanium and zirconium, onto which a thin layer of tungsten rhenium focal track is coated. The specific heat capacity of molybdenum is higher than that of a tungsten. The mass of the molybdenum anode is also lower due to its lower density. To increase the disc volume, the anode is backed with the graphite. Though it increases the weight, but it will be doubling the heat storage capacity. Molybdenum and graphite have lower mass density and makes the anode lighter and easier to rotate. So, some higher output X-ray tubes have radial slots cut into the anode disc to reduce the thermal stresses which are caused by repeated heating and cooling. and heavy duty X-ray tubes have graphite layer in their back of the anode disc. The anode disc usually has an beveled edge, and the angle of the bevel will be varying from 6 degree to 20 degree. The bevel is used to achieve the line focus principle. Then next is about stator and rotor. An external electromagnetic that is create a magnetic field to spin the rotor. Usually a copper cylinder is connected to the anode stem will be rotated by the stator magnetic field at high speeds, that is thousands of rate per minute. An induction motor system will be facilitating the anode's high speed rotation with the stator outside the vacuum envelope and the copper rotor inside. Usually, the anode disc is connected to a rotor and it is made up of copper bars which are arranged around the cylindrical iron core. These are electromagnets which are surrounding the rotor outside the glass envelope called stator. Both the stator and rotor is called as an induction motor. When the stator coils are energized, a rotating magnetic field is produced which induces the current in the copper bars of the rotor. This induced current produces an opposing magnetic field that causes this rotor to spin. Usually, the rotor will be rotating at a speed of about 30,000 to 9,000 revolutions per minute, and this will facilitate the electrons to bombard a constantly changing area of the target. Since the electrical conductivity of copper is higher, it will facilitate the induction of strong currents from the induction coil supply. The surface of the rotor is blackened to enhance its heat dissipation by radiation process. The rotor support is usually made up of a steel, and the positive high tension supply is made at the end of the rotor support, which is outside the envelope. A lower speed rotor will be operating from 50 or 60 Hz power and will be gives a rotation of about 3000 rate per minute or 3000 rotation per minute. This speed is too low for a short exposure, which is of the order of milliseconds. High speed rotor will be operating from 150 or 180 Hz power and will be gives a rotation speed of 10,000 rate per minute. If the speed of the rotation is increased, the heat generated at the focus will be spread over a larger area. A modern X-ray tubes will be employing a high rotor speed by increasing the frequency of the stator assembly or stator supply with the frequency multiplying the circuits. The X-ray machines will be designed so that the tube cannot be energized until the anode contains its full speed. This delay time will be incorporated in the exposure buttons. The power supply to the induction coil will be producing eddy current which causes the heating of this rotor assembly. The next is about anode stem. Usually this anode stem will be connecting the rotor to the anode and it is made up of molybdenum to limit the heat transfer to the ball bearings. Usually the anode disc is mounted on a stem that is attached with the rotor. The anode assembly will be rotating with the help of some of the bearings, and the system is the stem is made up of a molybdenum which is having a high melting point, that is 2620 degrees Celsius, and poor heat conduction. The molybdenum stem will prevents the flow of heat from the tungsten to the bearings of anode assembly due to its smaller cross section. Thus, the bearings are protected from the heat which may cause them to expand and bind. Higher the length of the stem, higher the inertia of the tungsten disc. So, more will be the load on the bearings. Hence, it is desirable to keep the stem as short as possible. Then, next is about focal spot. Usually, a smaller area of the anode where the electron beam strikes will heats it dramatically, that is up to 2500 degree Celsius. Then next is about bearings. Usually the anode assembly will be rotated with the help of some of the bearings which are made up of steel ball racers. The bearings are in the high vacuum environment and will be requiring special heat insensitive non-volatile lubricants. Usually the bearings are coated with a lead or silver and it will be acting as a lubricant. Actually, the commonly we use lubricants such as oil and grease that will not be used in these setups since it will be vaporized during heating and that will be destroying the vacuum. So, some dry lubricants such as graphite may wear off as a powder and it will also destroy the vacuum. So, the commonly we used lubricant is a metallic gallium alloy, that is it will be liquid at the room temperature. So, it has a low vapor pressure and good electrical and heat conduction. So, some rotor models will be using a sleeve designs in which the rotor is inserted into a hollow sleeve and the rotor has spiral grooves cut for lubricant circulation. So, in this the wear and tear is very less. So, when the X-ray unit is turned on, the motor alone is energized first for the few seconds until the rotor reaches its operating speed. Then a high voltage will be applied to the tube for the required exposure. So after the exposure, the rotor is slowed down quickly by a dynamic braking to avoid wearing in the bearings. Since the electrons are striking the whole circumference of the anode, no part of the anode will be attaining a high temperature. The heat from the tungsten disc will be dissipated by radiating through the vacuum to the walls of the tube and then into the surrounding oil and tube housing. The life of the rotating anode X-ray tube will be limited because of pitting due to the continuous electron bombardment on the anode surfaces. These changes will be due to the thermal stress and this pitting will be reducing the X-ray yield and it will be changing the spectral distribution. The decreased output results in excessive scattering of X-rays and increased absorption of X-rays by the target itself. A pitted anode will affect the electric field between the cathode and anode and so alter the size of the focal spot. Then it is about vacuum envelope. Usually a glass or a metal encloses that maintains a high vacuum, preventing the electron collision with gas particles on their way to the anode. The anode and cathode are housed inside an vacuum chamber. This is to ensure that the electrons do not collide with any particles on their way to the metal target. If there is no vacuum, there will be air and it will be creating an electron cloud and which helps in the damage of the total X-ray tube. The next is about protective housing. A lead-lined case which surrounds the envelope to absorb the stray radiations and provide electrical insulation and cooling. X-rays are produced in all directions, so the tube is surrounded by lead shielding. This is to ensure the safety of the operators and the recipients of the X-rays. Usually an adjustable window will be allowing a concentration beam of X-rays to escape and can be controlled safely. That is the advantages over stationary anode. Usually there are several advantages which is over the stationary anode over the rotating anode over stationary anode. First is superior heat dissipation. That is, rotation will be spreading the heat over a large area and it prevents melting. Next is higher intensity. That is, allows for a higher tube currents and produces a more intense X-rays. Next, handles higher workloads. That is, usually it is essential for demanding applications like CT scans and angiography. So usually this applications, usually where these X-rays are applied, it is usually this rotating anode system is applied in computer tomography, that is CT, and general radiography, that is in X-rays, and usually in fluoroscopic method. So these all are for the topics which are covered, and next we can look the next topic in the next class. Thank you.